Good day, Miss Prieto. Good day, classmates. We are the group that has been assigned to topic number 6, gas laws and computation. The gas laws are the relationship between different variables we use to describe gases, and there are 4. We have pressure, volumes which are generally measured as liters, temperature, and the amount. To move further, there are different gas laws tackled in this video: Boyle's law, Charles' law, Gay-Lussac's law, Dalton's law, Avogadro's law, combined gas law, and ideal gas law. These gas laws take a different form mathematically, and now let's begin. From Robert Boyle, we have first Boyle's law, also referred as Mariott's law, that tackles on the relationship of gas, volume, and pressure. They are inversely proportional. If the volume decreases, the pressure increases, and vice versa. The formula of Boyle's law is P1V1 equals P2V2, in which the left side of the formula is the initial set of conditions. We have initial pressure, the P1, and the initial volume, the V1, while the right side of the equation is the changed set of conditions where the new pressure and volume is P2V2. So for example, a 3-liter container has a gas pressure of 5.1 atmospheric pressure. If the volume of the container is increased to 4.6 liters, what will be the new pressure inside the container? So we have the initial set of condition, the 3 liters of container, and the 5.1 atmospheric pressure. Now the question is, what is the new pressure inside the container if the volume is increased or changed to 4.6 liters? Now this is how it goes. By using the formula P1V1 equals P2V2, let's substitute all the given data. P1, we have 5.1 atmospheric pressure times V1, 3 liters, equals P2 times 4.6 liters. Multiply 5.1 and 3, we have 15.3 equals P2 times 4.6. Now divide 15.3 to 4.6, we have 3.33, and that is the new pressure. So that is the Boyle's law. Now let's move on to the Charles' law. Charles' law, that is formulated by Jacques Charles, a French chemist. This law refers to the relationship of gas temperature and volume. They are directly proportional. If the temperature increases, the volume also increases, and vice versa. The formula of Charles' law is V1 over T1 equals V2 over T2, where V is the volume and T is the temperature. So for example, a 2.4-liter flexible container holds a gas at 300 Kelvin. What will be the new temperature if the volume is decreased in 1.5 liters? So we have the initial set of condition, the 2.4 liters of container, and the 300 Kelvin. Now the question is, what will be the new temperature if the volume is decreased in 1.5 liters? Now this is how it goes. By using the given formula V1 over T1 equals V2 over T2, let's substitute the given data. V1, we have 2.4 divided by 300, which is the T1, equals V2, we have 1.5 over T2. Then reciprocally multiply 300 to 1.5, we have 450. And multiply also 2.4 and T2, we have 2.4 T2. Divide 450 to 2.4, we have 187.5 as our new temperature. And so that is the Charles' law. Let's go on to another law, which is Gay-Lussac's law. Gay-Lussac's law, that was named from another French chemist named Joseph Louis Gay-Lussac, who formulated the law. Gay-Lussac's law, also known as Amonton's law, refers to the relationship of gas temperature and pressure. They are directly proportional. If the pressure increases, the temperature also increases, and vice versa. The formula of Gay-Lussac's law is P1 over T1 equals P2 over T2. So for example, the pressure of a gas in a container is 400 atmospheric pressure at 120 Kelvin. What will be the new temperature if the pressure is increased to 440 Kelvin? So we have the initial set of condition, the 420 atmospheric pressure and the 120 Kelvin. Now the question is, what will be the new temperature if the pressure is increased to 440 Kelvin? Now this is how it goes by using the formula P1 over T1 equals P2 over T2. Substitute all the given data, especially the initial condition. We have 400 over 120 equals 440 over T2. Then reciprocally multiply 120 to 440, we have 52,800, and multiply also 400 and T2, we have 400 T2. Divide 52,800 to 400, we have 132 as the new temperature if the pressure is increased to 440 Kelvin. And so that is the Gay-Lussac law. Let's move on to Dalton's law. Dalton's law. This law refers to the pressure exerted by an individual gas in a mixture, also called as partial pressure. The formulas of Dalton's law are: first, Pg equals Nm over Nt, where Pg is the fraction of pressure of a gas in the mixture, Nm is the number of moles in a gas, and Nt is the total number of moles in the mixture. Next step or next formula is Pn equals Pi Pg, where Pn is the fraction of pressure of a gas in the mixture, Pi is the total pressure of gases in the mixture, Pg is the fraction of pressure of a gas in the mixture. We have here the formula summation of Pi equals P1 plus P2 plus P3 plus and so on Pn, where our index represents as I equals 1, and Rn is the number of gases, and the Pi is the total pressure of gases in the mixture. For example, a container contains 2 moles of oxygen and 6 moles of hydrogen at a total pressure of 100 atmospheric pressure. What would be the pressure of oxygen and hydrogen in the container? So the first step, we use the formula Pg equals Nm over Nt, where Pg is the fraction of pressure of a gas in the mixture, Nm is the number of moles in a gas, and Nt is the total number of moles in the mixture. First, we should get the oxygen. Po equals 2 moles of oxygen over 8, which is the total 2 moles of oxygen and 6 moles of hydrogen. Now we have 0.25. The next, we have hydrogen, which is pH equals 6 over 8. Now we have 0.75 for hydrogen. Now the next formula we should use is Pn equals Pi Pg, where Pn is the fraction of pressure of a gas in the mixture, Pi is the total pressure of gases in the mixture, Pg is the fraction of pressure of a gas in the mixture. So first, we should solve P1, which is the oxygen, equals 100 atmospheric pressure times 0.25. We have 25 as the total pressure of oxygen gases in the mixture. The next, we should get first the hydrogen, the same step. So P2 equals 100 times 0.25. We have 75 total pressure of hydrogen gases in the mixture. Now the second step, third rather, is to check by using the formula summation Pi equals P1 plus P2 plus P3 plus so on plus Pn, where our index is I equals 1. So we have Pi equals P1 plus P2, where our Pi is the 100 atmospheric pressure given in the problem, and the P1 is our total pressure of oxygen gases in the mixture, while P2 is for the hydrogen. Add 25 plus 75. Now we have 100 atmospheric pressure is equal to the total pressure of oxygen and hydrogen gases, and that is the Dalton's law. Let's move on to Avogadro's law. Avogadro's law, formulated by Amedeo Avogadro, referred as Avogadro-Ampere's hypothesis. This law refers to the relationship of gas volume and number of moles. They are directly proportional. If the volume increases, the number of moles also increases, and vice versa. The formula of Avogadro's law is V1 over N1 equals V 2 over N2, where V is the volume and N is the number of moles of the gas. For example, we have a container with a volume of 10 liters hold 2.1 moles of gas. If the moles of gas is increased to 2.8, what will be the volume of the container? By using the formula V1 over N1 equals V2 over N2, so we have the initial set of condition, the TL that holds 2.1 moles of gas, substitute the data, and also the 2.8, now we have 10 over 2.1 equals V2 over 2.8. Reciprocally multiply 10 times 2.8, we have 28 equals 2.1 V2. 28 divided by 2.1, we have 13.33 as the new volume of the container. So that is the Avogadro's law. Let's move on to the next law, which is the combined gas law. Combined gas law. This law is derived from the laws of Boyle, Charles, Gay-Lussac, and Avogadro. It combines all the changeable pieces, pressure, temperature, and volume. The general formula of the combined gas law is P1V1 over T1N1 equals P2V2 over T2N2, where P is the pressure, V is the volume, T is the temperature, and N is the number of moles. A sample of carbon dioxide gas is contained in tank with a volume of 24 liters at 250 Kelvin at the pressure of 2 atmospheric pressure. The pressure is decreased to 0.8 atmospheric pressure, resulted to a temperature of 225 Kelvin. What will be the new volume of the container? So the general formula is P1V1 over T1N1 equals P2V2 over T2N2. Now we can eliminate the amount of moles because we have no moles in the given problem. So let's proceed. We have all the initial set of conditions, 24 liters, 250 Kelvin, and 2 atmospheric pressure. So we have 2 times 24 over 250 equals 0.8 V2 over 225. Multiply the P1 V1, 2 times 24, so we have 48 over 250, and then multiply also P2 V2, we have 0.8 V2 over 225. Reciprocally multiply 48 and 225, we have 10,800, and also reciprocally multiply 250 times 0.8, we have 200 V2. So divide 10,800 to 200, we have 54 as the new volume of the container. Now that is the combined gas law. Let's proceed to ideal gas law. Ideal gas law. This law is the combination of the laws of Boyle, Charles, and Gay-Lussac. Emile Clapeyron made the ideal gas law. The formula of ideal gas law is PV equals nRT, where P is the pressure, V is the volume, N is the amount of moles, R is the ideal gas constant, and T is the temperature. It is noted that R is always Avogadro constant, which is 0.08206. We have here an example, a nitrogen gas with a moles of 2.4 with a temperature of 200 Kelvin and a pressure of 5 atmospheric pressure. What will be the volume of the container where the gas is contained? So by using the formula PV equals nRT, substitute all the given data, we have 5 times V equals 2.4 times 0.08206 times 200. Multiply all nRT 2.4, 0.08206, and 200. Now we have 39.38888. Now divide 39.3888 to 5. We have the volume of the container, which is 7.8776. Now that is the ideal gas law. Overall, the different gas laws being tackled in this video are Boyle's law, Charles' law, Gay-Lussac's law, Dalton's law, Avogadro's law, combined gas law, ideal gas law. And I am Jora Largado, and my group mates are Florence Basay and Rustico Talaugon. Thank you for watching and have a good day.